Hello, my name is Zaid Al-Madin, and today I'm going to be talking to you about designing programs as well as analyzing programs. The first thing that we're going to talk about is the waterfall method. So the waterfall method was actually first introduced by Dr. Winston W. Royce in 1970. The waterfall method is a logical progression of steps that must be taken throughout a software's developmental life cycle. The first step of the waterfall method is the software requirements. This describes the potential requirements of the application and are methodically analyzed and written down in a specific document that serves as the basis for all future development. An example of this is the guidelines given to us by Mr. Truong, which describe our project requirements, what needs to be in our project, and so forth. The second step is analysis. During the second stage, the system is analyzed in order to properly generate the models and business logic that will be used in the application. The third step is design. This stage largely covers technical design requirements such as programming language, data layers, services, etc. A design specification will also typically be created that outlines exactly how the business logic covered in analysis will be technically implemented. An example of this is the inheritance diagrams made of the program before the start of the object project. In this, we show the design without actual code and give a description of how the program is going to work together conceptually. The next step we have is the coding phase, which is quite self-explanatory. This is the actual source code that is finally written, implementing all models, business logic, and service integrations that were specified in the prior stages. The fifth step is the testing stage. During this stage, beta testers and all other testers systematically discover and report issues within the application that need to be resolved. It is not uncommon for this phase to cause a necessary repeat of the previous coding phase in order for revealed bugs to be properly squashed. The last stage is maintenance. Once the application is ready for deployment to a live environment, the operations stage, the maintenance stage, entails not just the deployment of the application, but also subsequent support and maintenance that may be required to keep it functional and up to date. Now there are a couple pros and cons towards this model. So a pro towards this model is that it is very easy for new team members to familiarize themselves with the program by reading the documents. New team members and entirely new teams can easily pick up and join into a project as it is very well structured and it is very easy to follow. Another pro is it provides a structured and straightforward approach to larger projects. As I've seen in my own experience, when given a big task, it can be very daunting. Following these steps gives you a very structured and straightforward approach to allow you to delve into these projects without getting ahead of yourself. A couple cons of this method is that you may not necessarily know what the code requires. This can lead to multiple redesigns, multiple types of redevelopment as the code grows as you create it. You might not need something, but you might end up wanting something else. For example, I didn't know that I was going to use a menu-based output in my main, and to do this, I had to go back and redesign a lot of my design step in the waterfall method. Another con is that designers might not be aware of future difficulties at the start. There are many small issues or things that may not work together code-wise that you thought would work together conceptually, which you may not know at the start but find out later on in the waterfall model. The next subject that we're going to talk about in this video is a UML diagram. UML stands for Unified Modeling Language. So some background information on the topic. A standardized modeling language that UML is a standardized modeling language that consists of integrated diagrams that are used to help the visualization, construction, and specification between classes and an object-oriented system, without having to look at code. So it's very important to note this, that no code is actually involved. There are 13 types of diagrams, which are separated into two distinct groups. The first group is a structural UML diagram, and the second is a behavioral UML diagram. For the intents and purposes of this video, we are going to be focusing on class diagrams, which is one of the 13 types. So now let's look at the types of relationships between classes in a class diagram. So the first relationship is inheritance, which shows a relationship between the classes themselves. So in this, one class is the parent class, and one class is the subclass, which extends from the parent class. There will be an example later, which I can go and show deeper into this. The second type of relationship is association, which shows the relationship between the instances of the class. The third type is aggregation. This is where one class contains a collection of instances of another class. The instances of the other class can exist independently of the collection. Fourth type is composition, which shows a strong has-a relationship. A has-a relationship basically means that if you can put two words together, as in a dog has a cage, has a owner, and this relationship is used to describe the relationship between different classes. This class can contain one or more instances of another class. A difference between aggregation and composition is that the instances cannot on their own be created by the container constructor and destroyed by its destructor. Each relationship has a number beside it. If it doesn't, then the relationship is between itself. And the number represents how many instances of a class are involved in a relationship. This is called multiplicity. There are a couple rules that are associated with diagrams, and this helps to interpret what the diagrams are telling us. The first rule is that the rectangles represent classes. The second rule is that an is-a relationship, so this means that an example of this would be that chemistry is a class, is a subject. And so is-a relationships are shown between classes with an up arrow. Is-a relationship that involves an interface is shown with an open dotted up arrow. A has-a relationship is shown with a down or sideways solid colored arrow. And here in our example, we can see the first one. This shows that there is a interface involved between these two classes, and here we can see this showing that there is an is-a relationship between these classes. The last thing that we're going to be talking about in this video is program analysis. So what is the importance of program analysis? Program analysis works towards improving the program's performance while reducing the resource usage, as well as focusing on ensuring that the program does what it's supposed to. This can be done without running the program. This is known as static program analysis, or while running the program. This is known as dynamic program analysis. So let's list out what the importance of program analysis is. One, it improves the stability of the code. Second, it promotes efficiency. And third, it assists in the debugging of the code. A type of program analysis, something that's used very commonly in program analysis, is known as assertions. So assertions are something that are always expected to be true at a certain point in the program. If an assertion evaluates to false at a runtime, an assertion failure results, which typically causes the program to crash. These can be used to help programmers specify programs and to reason about the program's correctness. So an example below is that x is made to equal 1. So in this assertion, x is greater than 0, which is true. Now 1 is added to x, And now you can see that x is larger than 1, so this assertion proves to be true. The next thing we're going to talk about is preconditions. A precondition is a condition that must always be true just prior to the execution of some section of code, before an operation in a formal specification. If the precondition is violated, the section of code becomes undefined. Mostly, preconditions are used as guards or assertions within the code for security measures. So an example of this, or an example that you can think of, is what needs to happen in order for blank to happen. So what needs to happen in order for this method to run? What data type needs to be given? Does this number need to be above 0? Does this number need to be below 0? This is where preconditions come into context. An example is seen on the right, where int get deposit requires a precondition before it can run, as well as int withdrawal requires a precondition before it can run. The next thing we're going to talk about is post conditions. A post condition is a condition that must be true just after the execution of a section of code. This helps to assure that a piece of code executes as planned. So as seen on the right is the same example, except at the bottom of the int withdrawal method, you can see that there is space where a post condition would be ensured. This post condition would have anything to do with the money in the bank being lower than it was before, as a withdrawal requires a removal of a certain amount of money, and this is where post conditions can be used. The next thing we're going to talk about is efficiency, and specifically the different types of efficiency. So the first type of efficiency is the time it takes for a program to run, the CPU time. This refers to the number of machine operations required to carry out the algorithm. Arithmetic operations, comparison, data movement, etc. all take up time. The next is memory, and memory refers to the number and complexity of the variables used. Third, we talk about code reusability, how the code can be used in different situations. The more situations that one piece of code can be used, the more efficient the piece of code is, as you can call it as a method instead of writing it out and the program having to run through it every single time individually. The next is error and exception handling. This is how a program handles errors. This could be throw exceptions and such. A program would not crash with a simple error, which would in turn make it more efficient. The next is design logic compliance, which shows how easy a program is to understand and use. If you can't understand your program and it is hard for others to understand your program, then you definitely have an issue of efficiency on your hands. The next is data access and management optimization, using only what is needed. An example of this is importing classes. When you open a program, when you start a program, the reason why you're not able to access every single class, and you have to import math, for example, is for efficiency. By importing these, you are causing the program to have to look through more code and take more time to look through that class. This is why importing only what is needed and using only what you need is very important. To making sure that your code is efficient. The last type of efficiency is the use of data type and variables. So using data types and variables that are suitable to situations. A very common example of this is people using doubles instead of using int. A double takes up a lot more memory than an int does. While this may be tiny in comparison to the memory that a computer stores, in a larger scenario where you have thousands or millions of doubles compared to ints, they do add up and cause a bigger problem than you would think. Thank you for listening. I hope you learned a thing or two. See you next time.